the next step is to see how HO and HA relate to one another. We've already said that they overlap. They have to, because if each one goes from negative infinity to positive infinity, that means they must overlap. Before we see them overlapping, there's something that I need to explain to you, and it's easier to do this by looking at HO and HA separately. So here is a picture of HO, right? And we already know along the x-axis are values of the TS, right? These TS values go from positive to negative infinity. You've already learned that if your TS is larger than the critical value, and you get this critical value from a table based on your alpha, your level of significance that you choose. All right. So if you're choosing an alpha of 0.05, then we know that in each tail we have to have 2.5%. And the middle is going to be 95. And we look up this critical value in a table, and it tells you what the cutoff score is for your test statistic. So if this critical value, let's say, equaled 3, it means that your test statistic value must be larger than 3 in order to get into this rejection zone. Right? Now there is also, one over here. I just haven't drawn it because it gets complicated if you put too much on a graph. So we're just going to look at one tail and see what's going on. So again, your TS has to be bigger than whatever this value is. Okay, so this critical value is just a TS value. And so if this particular TS value is 3, and that's the boundary, right, that defines the rejection zone, then we call it the critical value. So if this is 3, your TS has to be 3.1, 3.2, just something bigger than 3. And then you know that you're in this part of the curve. Now, what do we call this part of the curve? We call it alpha. All right. Alpha, remember, we said is level of significance, but it's also the probability of making a type 1 error. And what that means is that if you're here, you're going to reject HO. However, you might still be a part of HO, right? You see that these values down here, although they're larger than the critical value, these values in theory could belong to HO. They are under HO. They could belong here, but they're just very, very unlikely. And that's why we reject HO. If it does turn out, however, that the TS is in fact one of these values and it belongs to HO, then we've made a type 1 error. So by measuring this area under the curve, we can determine the probability of making a type 1 error. And we know what this area is, right? If we're using alpha 0.05, this rejection zone area is 2.5, and the one that would be over here is 2.5. So the combined area is 5%. So if we get a TS here, we can say that the probability of our test statistic is less than 0.05, that's 5%, less than 0.05 under HO, but that also means that the probability of making a type 1 error is also less than 0.05, which is small. Less than 0.05 is small, but it's still a possibility. So alpha is the symbol that we use to measure this area and this area over here, right? If we had a critical value over here, we'd have alpha here as well. So together they make up the total alpha, the total probability of making a type 1 error. Now, if this area here is alpha, what would everything else have to be? Just ignore this tail for a second. All right, so if this is alpha, the total area under the curve has to be 1 minus alpha. So if we took the combined alpha, because you have one over here and one over here, that total area, subtract that from 1, and you get this middle part, all right? Because again, the total area under HO has to be 1 or 100%. So if you know what alpha is, right, the total alpha, this area here has to be 1 minus alpha. If alpha is 5%, this has to be 1 minus 5% or 95%. All right? So there's only two areas under HO. One of them is the area symbolized by alpha, and the other is the area symbolized by 1 minus alpha. If we are in alpha, this area here, a rejection zone, that's the probability of making a type 1 error. All right, that is where you would reject HO, but it could be a mistake. We don't know, but it could be a mistake, a type 1 error. 1 minus alpha is the area where you would make a correct decision. 1 minus alpha means that your TS must not have been bigger than the CV. Your TS was smaller than the CV. So you did not reject HO, you retained it. And if you retained it, and in fact it was a correct decision, that area is measured by 1 minus alpha. So notice that alpha and 1 minus alpha are probabilities. All right, they are areas under HO. Alpha, 1 minus alpha. Together they make up 1 or 100%. All right, so your two areas are 1 minus alpha and alpha. They represent the probability of either correctly retaining HO, that would be 1 minus alpha, or incorrectly rejecting HO, that would be alpha, probability of making a type 1 error. Together they sum to 1. Now let's look at areas under HA. Again, there's two areas. All right, and again, they have to add up to 1 or 100%. So if you have a critical value, that critical value is also going to appear somewhere on HA, right? Because HO and HA overlap. They both extend from negative to positive infinity. So when you get a critical value, that critical value is not only going to be on HO, it's also going to be on HA. If, let's say, your particular TS, the one that you calculated, is not bigger than the critical value, then we know it's going to be somewhere in here, right? It's going to have to be, because just like HO, these values go from negative infinity to positive infinity. So if it's below the critical value, it's going to be on this side. Okay, so you have a TS here. Now it's under the critical value, so what would we have done? We would have retained HO, right? But you see how these values could also belong to HA? They fall under the HA curve. So if you retain HO, as you would do, all right, if you retain HO, it means that you could have made a correct decision, but maybe you've made an incorrect decision, and maybe your TS actually falls under HA. That is called making a type 2 error. That's where you retain HO, but you should have rejected it. It's called a type 2 error, and the symbol for calculating the probability of a type 2 error is beta, and it is measured by this area here. So if we were to calculate this area, that would be the probability of making a type 2 error. Now, what if your TS is larger than your critical value? Well, if it's larger, that means it must fall on this side. And if it falls on this side, it's a high probability event on HA. And so you would more than likely be making a correct decision. But I say more than likely because these are all just probabilities, right? So if you were here and you made that correct decision, that area is measured by 1 minus beta. So this is the probability of making a correct decision. In other words, saying that you have a treatment effect, and in fact, you do. This area here is where we want to be. We want to be in the area that says we've made a correct decision. So in order to be in this area, the first thing that has to happen is our test statistic has to be bigger than the critical value. And if it is, then there's a probability that we're in this correct decision part of the curve. It's measured by 1 minus beta, and we have a special name for it. It is called power. All right, so power represents the likelihood that we are in this highly prized area, correctly rejecting HO. Okay, again, this area plus this area adds up to 1 or 100%. Okay, so we've just seen that there are two areas under HO. They are alpha and 1 minus alpha. There are two areas under HA. They are beta and 1 minus beta. Now it's time to see them overlap. All right, and this is just a reminder down here of the two areas, right, under HA. And they are the probability of incorrectly rejecting HO, so that would be a type 2 error, and the probability of correctly rejecting HO, right, and that would be 1 minus beta. The two areas have to sum to 1. Now let's look at them overlapping. So here's HO and here's HA. Could I have flip-flopped them? Absolutely. If I flip-flop them, though, and I put HO over here and HA on this side, then these symbols need to flip-flop as well. So this symbol here has to go over here. This one has to flip-flop over to that side. And the same thing, these two areas would have to change, okay? So just remember that, because that could be a really good quiz question or test question, etc. All right, so if let's say HO is over here and HA is here, it means that we are only going to look at this part of HO. If we were to flip-flop and HA is actually over on this side here, then we would be looking at this tail, all right? So here we're saying sampling error plus something else, that treatment effect, is going to increase the value of our TS in this direction. And that's why we put HA here. Okay, so again, if we're testing a hypothesis where we're expecting our TS is going to be more and more positive, then we draw HA on this side. If we are calculating a test where we expect our TS to be negative, then we're going to put HA over here and we're going to look at this tail. All right, don't worry so much about that. That has to do with something we're going to learn in our next lecture, which is about directional tests. Right now, it really doesn't matter which tail we're looking at, but since we are looking at this one, we're going to put HA over here. All right? Okay, so here's our HO. What's the first thing we do? Well, if we had SPSS, we wouldn't be doing this at all, right? If we had SPSS, remember, gives us the exact probability of making a type 1 error. It tells us exactly what the probability is for our test statistic. And so as long as it's less than 0.05, we go ahead and reject HO, and we never need to look at these pictures. But you're better than just looking at SPSS. I want you to understand the behind the scenes, what's going on behind the scenes, so you have a deeper appreciation and understanding of our hypotheses and the consequences of making correct decisions and the consequences of making errors. Okay, so let's say our test statistic is greater than the critical value, so it's in this area. Now, it could belong to HO, right? Because these values are under the curve for HO. But it's pretty slim, right? These are all low probability events on HO. They are higher probability events under HA. So that same TS value although it's low here, is a high probability event under HA. And that's one of the reasons why we reject HO. We say it's too unlikely to belong to HO. So we're going to reject it in favor of HA. But that means that you're in one of two areas. By rejecting HO, you might be here or you might be here. Now, if you're here, that's the probability of making a type 1 error. If you're here, that's the probability of making a correct decision by rejecting HO, correctly detecting the treatment effect. And what do we call that? Remember we gave this area a special name? It's called power. And that's something you're going to learn about today as well. Now, what if your critical value is below the CV? So it's less than the CV. Then there's also two areas you could be in. You might be in this area here called beta, might be there, or you might be in this area, 1 minus alpha. 1 minus alpha we don't have a special name for, but it's the probability of correctly retaining HO. All right, these are high probability events under HO. This is the probability of correctly retaining HO. This area, if you happen to be here, and of course you won't know, right? You won't know if you are here or here. But if you are here and it's under HA, then that is the probability of a type 2 error. You're saying something belongs to HO, but in reality, it actually belongs to HA. Okay? So it's the probability of a type 2 error. And again, remember that areas need to add up. So beta and 1 minus beta add up to 1. Alpha and 1 minus alpha add up to 1. Now, hopefully, you can see that there are 4 areas, and those 4 areas represent the 4 possibilities of hypothesis testing. I said that there were 2 types of correct decisions. All right. This is the probability of correctly retaining HO. In other words, correctly recognizing that there's sampling error. And that's it. This is the probability of correctly rejecting HO, correctly detecting a treatment effect. This is the probability of a type 1 error, and this is the probability of a type 2 error. And generally speaking, this is the one we care about. Remember we talked about type 2 and type 1 errors, right? Type 1 errors are the errors that most likely would appear in the published literature. And so they have the potential to influence a lot of people. Type 2 errors tend not to get published because these are non-significant results. And so they affect your lab, but if they're not published, then they only affect your lab. All right. So these are some reminders. So if you're printing out these slides and everything, you'll see these on those slides. If we retain HO, that is what happens when we're less than the critical value. Then we're either here or we're here. All right. And we don't know which one we're in. If we reject HO, it's because our test statistic was on this side of the critical value, and that means we're either here or we're here. And again, we don't know which one we're in, but we can at least, calculate the probability of being here. And that is the area that we care most about. All right. Now it's time to reiterate something that I said before. I think this was in lecture 1 of chapter 7, but it's really important. When we get a significant test result, so we calculate a TS and we determine that it's significant. So what that means is that we have sampling error plus something else. All right, so there's a tendency for people to automatically conclude that our statistics are telling us that our specific hypothesis is correct. And that's just not true. Our statistics don't understand words. They don't understand what your specific hypothesis is saying. The only thing that your statistics are telling you is that you probably have sampling error with something else. Wrong, by the way. I should have popped that up sooner. I'm not saying I'm wrong about what I just said. I am saying that this statement is wrong. So if we get a significant result and reject HO, this means our stats have supported our specific hypothesis, right? And that's wrong. All right. And it's because our statistical test does not understand words. It doesn't know what our specific hypothesis was. All that our stats are telling us is that we have something more than sampling error. Statistics do not tell us what that something is. That is our job. So you're the researcher. These are your readers, okay, or your professors or your classmates. And it's your job to say, look, I found significant results. And I'm going to convince you the reason why I found significant results is because that something else happens to be my manipulation. It was because of my independent variable that we saw significant effects. And that is sometimes not an easy task because a lot of times when we do research, we'll have confounds. Other explanations that could explain our results, other explanations that could be that something else. All right, that's something you learned at the beginning of the semester. All right, when we manipulate an independent variable, we're hoping that that is the only reason making the groups different and making the groups behave differently. But often we have confounds, and these are other variables. They started off as extraneous variables, but then they became confounds when they became different for our groups. And that means that when we see a significant difference between, let's say, group A and group B, we have to argue that it was only because of our independent variable and that there were no other confounds that could explain the results. Right? So you see how that's not easy to do.